Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of real analysis. Our discussion is continue on chapter number 3, numerical sequences and series from Principles of Mathematical Analysis by Walter Rudin. Lastly, we discussed theorem 3.10 A part. In today's lecture, inshallah, we will discuss its B part. The proof of this theorem is very simple and straightforward. Uh, Firstly, I will discuss its proof, and in the last, I will discuss some important facts related to the proof. The statement says if Kn is a sequence of compact set in X such that Kn is superset of Kn plus 1 for all n belong to positive integer, or you can say n is equal to 1, 2, 3 up to so on. Kn is superset of Kn plus 1 mean every previous set is a superset of the next set. In other words, if you put n is equal to 1, this gives K1, K1 is superset of K2. If you put n is equal to 2, this gives K2 is superset of K3, K3 is superset of K4, and up to so on this chain is continue. So the first information in the theorem is given the set is compact set. What is compact set? I have already discussed the concept of compact set in chapter number 2. Otherwise, at the end of the lecture, I will discuss something about compact set. For the time being, we will not use this concept directly. So the first information is that every Kn is a superset of Kn plus 1. The second information is if the limit of the diameter of Kn is approaches to 0. This is second information, and this we have to show. Then the infinite intersection of these Kn consists of exactly one point. In other words, we have to show this intersection n is equal to 1 say infinity Kn. This is equal to some singleton set like this. We suppose this infinite intersection, as you know, the intersection of two or more than two sets is always a set. So we says this intersection is equal to some set K. Now, by the corollary of theorem 2.36 in chapter number 2, which states that if Kn is a sequence of non-empty compact set, this you can see this corollary from chapter number 2. It can be stated as if we have a Kn which is a sequence of a non-empty compact set such that Kn is a superset of Kn plus 1 for all n belong to set of integers, positive integer, then this intersection is always non-empty. So according to this corollary, as I have put this intersection equal to K, it means this K is non-empty. Now I have to show this K is non-empty, but it should be a singleton set, just contain a single point. This is our requirement. But we will work on the contrary. We suppose on the contrary that this set K contains more than one point. You can say your set K contain a point A, B, C, etc. Suppose. So if this set K contains more than one point, then clearly the diameter of this K is greater than 0, because the singleton set is the only set whose diameter is exactly equal to 0. If K is singleton, then clearly its diameter is equal to 0. But when you suppose this K is consists on two or more than 2 points, then its diameter could not be 0. This will be a positive. As it is given that for each n, kn is superset of k. Now focus on this set, how kn is greater than k. What was k? K is the intersection of kn. N is equal to 1 to infinity. So this intersection gives k. As the intersection is always the smallest set, it is always a smallest set. It means your k1 is superset of k, your k2 is superset of k. It means all of these kn will be superset of k. So that's why I have written here kn is superset of k. So that if kn is superset of k, then diameter of kn is greater than or equal to diameter of k. In the last lecture, I have discussed that if A set A is superset of B, then diameter of A is always greater than or equal to diameter of B. So according to this result, if Kn is a superset of K, then diameter of Kn is greater than or equal to diameter of K. But diameter of K is positive. How is this positive? Because we suppose K contain more than one point. That's why its diameter is positive. So if its diameter is positive, this will be greater than 0. This implies diameter of Kn is greater than 0. But this contradicts with the fact that diameter of Kn is equal to 0 as n approaches to infinity, because it is given in the statement that if the diameter of Kn as limit n approaches to infinity is 0, then we have to show that this intersection is non-empty, is a singleton set. So when we suppose this set K contain more than one point, we reach with the contradiction that its diameter is positive. Diameter of Kn is positive. Hence our assumption is wrong and K consists of exactly one point, and it completes the proof. Now there are some important facts related to the theorem. I hope you have read in the elementary real analysis course uh, following statement: classical Cantor intersection or nested interval theorem. Actually, the proof that actually this theorem that we have proved now, this is the generalized form of generalized form of Cantor intersection theorem. This is the generalized form of Cantor intersection theorem available in the book of Walter Rudin. What is the difference between classical and a generalized form of Cantor intersection theorem? The first difference is that in the classical Cantor intersection theorem, the statement just involve closed and bounded intervals, while Walter Rudin discuss this statement for compact set. Compact set is a broad term than the bounded and closed interval. The second difference is that in the classical Cantor intersection theorem, we discussed our statement for set of real number R, but Walter Rudin discuss this form for every metric, for any metric space X. So these are the two difference between the generalized form and the classical intersection theorem. So just for your convenience and elaboration, I am discussing here classical Cantor intersection theorem. Although this is not part of this proof, this is just for your concept. This theorem says a nested sequence of closed intervals has a non-empty intersection. The first word that may confuse you: what does mean by the nested sequence? Uh, Nested sequence. A collection of sets is called nested sequence if each successive set is contained in the previous one. This collection is called nested sequence. For example, more precisely, we can write I1 is a superset or equal to I2, I2 superset equal to I3, up to so on. This procedure is continue. So this sequence of interval shows nested sequence of interval. Further about this sequence of interval, it is given that In is a non-empty closed intervals in R. So this is the difference from the statement given in the book of Walter Rudin. Walter Rudin just says these In are actually the compact set, and classical intersection theorem, these are the non-empty closed interval in R. Then we have to show that this intersection is non-empty, and in addition, if the limit of the diameter of In is equal to 0, then this intersection consists of exactly one point. So I will elaborate this concept by a simple example. I will just take first of all I will take a sequence of nested closed interval. Take In is equal to, this is the closed interval whose first point is minus 1 over n and the second one is 1 over n, and n is a positive integer. When you take n is equal to 1, here the first interval is I1 minus 1 to plus 1, second interval is I2 minus 1 by 2 to 1 by 2, third is minus 1 by 3 to 1 by 3. Up to some procedure is continue. We can see that I1 is a larger set in the interval. This start from minus 1 to plus 1. Clearly I2 is a smaller set than I1. I3 is a smaller set than I1 and I2. So I1 is a superset of I2, I2 is a superset of I3, up to so on. So this is the nested sequence of closed interval. It means this set of intervals shows the example of nested sequence of closed interval. What is the next? Next I have to show if this intersection is non-empty. So we can check that this intersection will be non-empty. From the number line, you can, if you write here, this is minus 1 to plus 1. This is my I1. Minus 1 to 1 by 2, this is my I2, and minus 1 by 3 to plus 1 by 3, this is I3. And from both sides, if you shrink this interval, this approaches to the number 0. It means their intersection is non-empty. Now if I calculate its diameter of this interval is simply given by, what is our interval? Our interval is minus 1 by n to plus 1 by n. How can we calculate the diameter of the interval? Just by taking the difference of upper value to the lower value. So this gives 1 by n minus 1 by n. This is 2 over n. So when we take limit n approaches to infinity, its diameter is 0. So its intersection is non-empty, diameter is approaches to 0. Hence, this intersection just contain a single point, and from the figure you can observe that all of these points approaches to the single point 0 whenever you shrink this interval. That completes the statement of Cantor intersection theorem. Further, some of important things you can read here. A subset of Rn is compact if and only if it is closed and bounded. It means in a classical Cantor intersection theorem, the statement is that our intervals are closed and bounded. So by Hahn-Bohren theorem, these are compact set. So it means classical intersection theorem is the special case of generalized form. Further, a closed bounded interval is always compact, but it remember that a closed set may not be compact. For example, this is a closed set. How this is a closed? We know from a metric space or topology, a set is closed if it contains all of its limit point. So this set contains all of its limit point, that's why it is closed, but it is not a compact set, because for compactness it should be bounded. You can notice that this set is not a bounded, this is unbounded set. So this set is just a closed but not bounded, but closed and bounded is always compact. Anyhow, the general definition of compact set, but I am not delving in this definition in the detail. Just for your convenience, I have written this definition. A subset K of a metric space is called compact if every open cover of K has a finite subcover. and this definition I have already discussed in chapter number 2. So I hope now you have a clear understanding about today lecture. This is very simple and easy, and this gives the complete proof and complete concept of today lecture. So see you in the next lecture. If you find this video helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.